Hello, today's talk is on independence. It's video 7 in my little mini series of probability measure. And let's just jump right in. So here we have let A and B be events in our sigma field such that the probability of event A is positive. So remember that this sigma field is actually associated with a sample space of some sort. That's often left out, but it's implied. And so if the probability of event B given A is just the probability of B, then we say B is independent of A. But also note that if the probability of B is strictly positive, then we can say this. Then if you go through the math here, and then here B is independent of A, so those cancel, and we just get that actually A is independent of B. And that's a true statement. If B is independent of A is independent of B. And so the definition of independence is this, that if we have events A and B in our sigma field, and if they're independent, then the product of their intersection is equal to the product of their individuals. That's probability of A times the probability of B. This extends to several events in our sigma field, and they're independent if this relationship holds for all possible combinations. So this is a AJ1 to AJK, and so that's a way of saying that maybe we're looking at all combinations of pairwise and then three-way and then four-way, and this has to hold for all equations. So two-way combinations, three-way, four-way, and sometimes the word complete independent or mutually independent is used, but really it's just independent, and all these have to hold. So how many equations are here if there's n? Well, we have to have all two-way combinations, three-way, four-way, five-way, up to n-way. And that is this. So there's this many equations that we have to check for these events to be independent. Okay. So here's another definition. If we have events AJ, in events AJ, they're called pairwise independent if the two-way combinations satisfy this relationship. Okay. So one note is that independence implies pairwise, because you have n events that are independent. That means all possible combinations satisfy this type of relationship, even the two-way. Well, that means they're pairwise independent. But, and I have sort of a simple, silly example right after this. I'm going to show you that pairwise independence doesn't imply independence. Okay, so here's the example. We have a sample space with 4 outcomes. Each individual outcome is probably as 1/4. We create the events 1, 2, 1, 3, and 1, 4. And then notice that all the pairwise interactions are just 1, and the three-way interaction is 1. So now if we look at their individual pairwise comparisons, so A1 intersect A2, well, that is equals the product of these events, and well, it holds for all possible two-way combinations. So events A1, 2, and 3 are pairwise independent. Okay, but if we look at their three-way intersection, which is again 1/4, that does not equal the product of their individual probabilities. So this means pairwise independence does not imply independence. Okay, independence carries over to sigma fields. So if we let U1 and U2 be sub-sigma fields of U. So here U is associated with our sample space, and this is a sigma field associated with it. Now if we break this up into sets that are sigma fields themselves, then they're called sub-sigma fields of U. So now we have 2 sub-sigma fields, and they're independent if this relationship holds for all events in their respective sub-sigma fields. So then those two sigma fields are independent. Okay, and more generally, this is true for if you have n sub-sigma fields, they're independent if this type of relationship holds. And this is and each of those are the events in the respective sub-sigma field. So now this is a little bit more powerful than just the looking at in events. The way that you pick an event in a sub-sigma field, this can be like looking at all the possible n-1 type relationships, like the true independent formula that we have, or pairwise, the way you manipulate what events you pick in the sub-sigma field. So this is a pretty complex statement. So now let's look at compound experiment. So if we let experiment EJ, so there's two experiments, E1 and E2, and they each have their own sample space and their own sigma field associated with it. So for example, if we roll a die, that, and then we pick it up and roll it again, then we have two experiments that we think are independent from one another. But that's in a second. So what does the compound experiment S look like? So S is our sigma field of this compound experiment, and then we represent it by S1 cross S2, which are these tuples. So the first component are only outcomes from experiment 1, and the second tuple is only experiments from the experiment 2. Okay, so that's our sample space. So now how do we create a sigma field associated with this sample space? Well, what we do is we create we create a class of subsets of this compound sample space, such that the first outcome is only from experiment 1, second one are events from experiment 2. Then we we generate a sigma field associated with this class of sets. And then what this means is that in a previous video, we create all possible sigma fields that contain this. We take the intersection of those, and then that's the minimal sigma field associated with this class of events. So this is so this combination S, which is here, and the sigma field associated with this subclass, you call U, that's a measurable space. But it specifically refers to compound experiments. So we're going to call that a product measurable space, because it's kind of like the product of two random experiments. And so you can rewrite it like this, and that lets you know that we have two experiments. Okay. Now, whenever we have if we can create a measure on this sub-sigma field, more specifically the probability measure, which says the probability of this is 1, then we have a probability of space associated with that. Well, if these are compound experiments, how do we find this P that creates this probability space on this product measurable space? Okay, so that's, well, all right, more in a second. So experiments can be independent also, and if these two experiments are independent and we have sigma fields associated with each of those experiments, and remember that these are sub-sigma fields of the U. So on the back page, U was, remember we created this class and we generated a sigma field. So these are sub-sigma fields of this. Now they're independent if this relationship holds, okay? But the event B1 is very specific. It's A1 cross S2. So you always put the sample space of the second one. Remember, we're dealing with compound experiments. So B1 it's associated with experiment 1. And B2 is of this form. So these are events in the second experiment. So if this relationship holds, then we say that those events are independent. And I'm going to restate that. So events A1 cross S2 really refer to E1 alone. Okay, so if we use the silly dice rolling example, so on the first roll we roll a die, and let's let A1 be the event that it's an even number on the top. And we're crossing it with the entire sample space of our second roll. So this is saying, what's the probability that we roll an even number on the first roll and we roll a 1, 2, 3, 4, 5, or 6 on the second roll? So really, this is dealing with events in experiment 1 alone, because this becomes irrelevant. And the same way here, that if you're crossing it with the sample space of 1 crossed with events in experiment 2, really this is talking about event 2 by itself. Okay. So this is 2 experiments, but it's really straightforward to generalize this to say n independent events. So if you have n rolls of that die, or n flips of a coin, or you can create your own independent events, it's going to be easy to generalize this, that they're independent. So now I've glossed over one thing, and I think it doesn't really fit into this little thorough beginning mini-series on probability measure. But here, what usually happens is you think the experiments are independent, meaning the flips of a coin or drawing a card with replacement are all independent. So what you do is you create these probabilities for each experiment, okay? And then you create it, then you set up, you induce this relationship, you make it true, because we want the experiments to be independent, okay? But the true P associated with our compound space is not necessarily just the product of those individual probabilities. There's a way to extend each of those random experiment probabilities to the overall compound space. And the way you do that is with this theorem. And it's actually not a difficult thing to do. We're not going to cover it here. And so if you want to know more about that specifically, I'm going to refer you to here. Hopefully I've given you enough background on independence, and you can have independent events, independent sigma fields, independent experiments. Okay, well, that's all I have for this talk. Hopefully you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. The next talk will be on random variables. And what is so interesting there, random variables are technically set functions onto or into the real number line. Well, that's going to be the next video. I'll talk with you later. Bye.